Gravity, a Heavy Story, Part 1. On a small world known as asteroid B612 lived the famous Little Prince. Now one day the Little Prince wanted to know, how fast does he need to throw a rock so that it could leave his world or escape? And for that matter, how fast would he need to throw his rock so that it orbits in a circle and comes right back again? Now, the Little Prince has all the time in the world, so he studies physics and knows that the gravitational energy equation relates two masses separated by a distance s, and the negative sign tells him that would be the energy that that the two masses lose by being an s distance apart, or how much energy you would need to add or pay for them to be separated infinitely far away. Let's do an example. Say the Little Prince drops his rock, mass m, to the surface of the world. The rock is a initial distance from the center of the world, si. The surface is a distance, sf, from the center of the world. The energy lost as the rock falls would be gravitational energy final minus gravitational energy initial, rearranging the algebra. Well, the final distance is the radius of the world. The distance it falls is the distance h. So looking at the math, s final minus s initial falls a height h. Substituting in s final for r, then we get this result with all these variables. But we can relate this to our familiar mgh equation for loss of gravitational energy. If we times this equation we have by r over r, we'll get the mass of the rock times gmr squared. And then if we realize that if the radius of the world and the initial height dropped are not that much different in size, then our equation collapses down to our familiar mgh. Be sure to derive this. Notice we made a substitution for the lowercase g, the gravitational acceleration, relating to the gravitational constant, the mass of the world, divided by the radius of the world squared. Where'd that come about? Well, you know the force of gravity is equal to mg, and by Newton's law, we can relate that to g, the product of the two masses divided by their separation squared, which means that gravitational acceleration can be related to the mass of the world, the size of the radius of the world squared, and the gravitational constant. So the Little Prince can figure out the gravitational acceleration if he knows the mass of the world, or vice versa. Now, to figure out the speed he would need to throw a rock, the minimum speed he would need to throw a rock or any object so that it can escape from his world, he would start out with a rock at some initial height, let's say the surface r, out to as far away as he'd like. How far do we want to go? Well, let's just say infinitely far away. What initial speed would get him so the rock can go infinitely far away? That would be our minimum speed or escape speed. Any speed more than that, and it keeps on going. What does it mean to say it's infinitely far away? Well, at infinitely far away, the speed will approach zero. So we have just enough speed for it to go as far as we'd like without it falling back again. So now we'll try to figure out the energy equation. We know we're increasing our height and decreasing our speed, which means we're talking about a change in gravitational energy and a change in kinetic energy, which adds up to a change in the total energy, which is zero if energy is conserved. Well, knowing that our gravitational energy is increasing and our kinetic energy is decreasing, let's put those on opposite sides of the equation, increasing on one side, decreasing on the other, solve for gravitational energy relating to our kinetic energy, cross out our masses, setting s final to infinitely far away, s initial to the radius of the world, crossing out the masses because gravity scales with mass, and we get our result that we'll rearrange to solve for the minimum speed or the escape speed needed for the Little Prince to throw any old object he'd like he would know the speed that would have needed for the minimum speed needed, or the escape speed. Any speed greater than this, and the object keeps on going, infinitely far away, never to fall back again. He could calculate what this is if he knows the radius of the world and the mass of the world. Well, if he walks around the circumference of the world and measures that, diameter times pi is equal to the circumference, he knows that the radius of his world is 1 kilometer, but he doesn't know what the mass of it is. How can he find that? We'll see in Lesson 3 of the gravitational energy 3 ways to find it. Now onward to Lesson 2.